Imagine a scenario where a rocket hurtles through space at the speed of light, encountering an opposing force that will destroy it completely. What energy is released in this intense process? Well, according to Einstein's mass energy equation, it's equal to mc², where m is the mass of the rocket and c is the speed of light. That means all the mass of the rocket will be converted into energy. Have you ever asked yourself, why is this the case? Why does mc² give the energy, and how can you prove it? We can see that there are similarities between the kinetic energy equation and Einstein's mass energy equation. That makes us wonder, what is the relationship between the kinetic energy equation and Einstein's mass energy equation? So let's break this down using the kinetic energy equation to understand the relationship between the two equations. Consider a rocket of mass m moving at a velocity of v meters per second. To understand how this equation relates to the rocket's kinetic energy, imagine a hypothetical scenario where all the rocket's kinetic energy transforms into work. By this, we can calculate how much work the rocket can do, and since work is equal to energy, we get the kinetic energy of the rocket. To calculate this work, we need an opposing force that acts uniformly and continuously until the rocket stops entirely. So, as the rocket approaches the force field, let's assume the force is equal to the magnitude of the rocket's momentum, mv. This simplification helps us understand the process more clearly by giving a convenient value for the opposing force rather than taking some random value. Since force is equal to momentum's magnitude, the rocket takes precisely 1 second to come to a complete stop, which you can verify by looking at the equation. Force equals the rate of change of momentum. Here, the rate of change is with respect to time. Therefore, force is the change in momentum per second. So this force decelerates the rocket from velocity, meters per second to 0 meters per second, within this 1 second interval. To compute the work done by the rocket, we need two factors: the opposing force and the rocket's displacement during this force's action. By cleverly choosing the force equal to momentum, we have information about initial velocity, acceleration, and the time it takes for the rocket to stop. Utilizing the second equation of motion, we calculate the displacement as half of the velocity. Now we have the equation for kinetic energy. However, we chose an artificial scenario where the value of the opposing force was taken to be equal to momentum and the force acted uniformly throughout the process. What about cases where the force's magnitude and action on the rocket are random? According to the conservation of energy, if one case is proven, then all cases are proven, as the object's kinetic energy is the same irrespective of the opposing force. As the opposing force increases, the displacement decreases, and vice versa. Hence, we get the equation for kinetic energy for all cases. Now for the climax, let's use the kinetic energy equation to validate Einstein's famous mass energy equation. Imagine the same example with a rocket of rest mass m moving at the speed of light, c. Assuming the opposing force is of magnitude mc, the rocket's momentum should be 0 at the end of 1 second. But in this, can we understand that instead of the rocket slowing down, the mass of the rocket gets converted into energy uniformly until the rocket disintegrates entirely? When we calculate the total work using force times displacement, we get force is equal to mc and displacement is equal to c meters. Instead of slowing down as in the regular case, the opposing force disintegrates the parts of the rocket that are exposed to the force, and the rest of the rocket flies with the same velocity without slowing down, yielding Einstein's mass energy equivalence equation. There you have it, a simple derivation of Einstein's famous mass energy equivalence equation using the kinetic energy equation. If you found this video helpful, please like, share it with your curious friends, and subscribe for more intriguing content.